This section examines the fuel supply system. The purpose of any fuel supply system is to deliver fuel to the engine in a form in which it can mix with air to form a combustible mixture. The fuel must be finely atomized to mix with the air. This is why injection systems deliver the fuel under pressure. The EFI system is a circulation system. Fuel is drawn from the tank by a fuel pump and delivered to solenoid-operated injection valves. Fuel pressure at the valves is maintained by a fuel pressure regulator, and excess fuel flows back to the tank through a return line. The fuel filter is directional. It is fitted between the pump and injection valves to stop contaminants reaching other parts of the system. The fuel pump can be mounted externally on the chassis frame or submerged in the fuel in the tank. It is electrically operated and electronically controlled. It is driven by a permanent magnet electric motor, a sealed unit integral with the pump. Fuel flows through the pump and around the electric motor when it is running. There is never an ignitable mixture inside the pump housing, so there is no danger of explosion. The pump delivers more fuel than the maximum requirement of the engine, so pressure in the fuel circulation system is maintained at all times. A fuel pressure regulator maintains fuel pressure between the pump and the injectors. In multi-point injection systems, the fuel pressure regulator has an inlet connection from the fuel rail and an outlet that lets fuel return to the tank. A control diaphragm and pressure spring determines the exposed opening of the outlet and the amount of fuel that can return. So the strength of the pressure spring determines fuel pressure in the fuel rail and keeps it at a fixed value. However, the pressure in the intake manifold varies considerably with changes in engine speed and with load, so the pressure drop across the injector must also be taken into account. For any injection duration, if fuel is held at constant pressure, then as manifold pressure varies, so does the amount of fuel delivered. That means fuel pressure must be held constant above manifold pressure. This is done by sealing the spring housing of the pressure regulator and letting it sense manifold pressure via a connecting hose. Then, when the manifold pressure alters, so does the fuel pressure. When manifold pressure is low, as at idling, fuel pressure is low. As manifold pressure rises towards open throttle, so does fuel pressure. Since the injectors are all subjected to the same pressure, they all inject an equal amount of fuel. The quantity of fuel delivered is thus controlled very accurately by the pulse width of the injector. Manifold pressure sensing is not required in throttle body systems, as the injection occurs above the throttle plate at atmospheric pressure. So fuel pressure is determined by the force of the regulator spring acting on the diaphragm. The injectors are sealed into the manifold by O-rings that prevent air entering at that point. The O-rings, together with plastic caps on the injector nozzles, also act as a barrier to heat being transferred to the injector body. For a short time after an engine is switched off, engine temperature keeps rising, and that can cause excessive vapor in the fuel lines. This pump stops this with a non-return valve on its outlet, which maintains the pressure in the fuel line during that short time. This pressure will decay over about 20 to 30 minutes, but it ensures effective hot starting characteristics. When the engine is running, the circulation of fuel ensures cool fuel is being delivered at all times, and vapor formation is prevented. The pump control circuit normally allows the pump to operate for a few seconds only when the ignition is switched on, and thereafter during cranking, and when the engine is running above a specified minimum RPM.